Welcome back. We talked about early decomposition step. Then we said that it's um, it's useful for getting the inverse of a matrix. Now we're going to move on to the next method, which is the Gauss-Seidel method. So the Gauss-Seidel method for finding or for solving linear algebraic equation is an iterative approach for solving. Okay, there's a question. The decomposition method is manual. Is it okay to use Matlab? Yes, you can actually use, yes, you can use Matlab or Excel VBA to decompose the matrix. So we are going to be discussing about using software numerical tools to solving linear algebraic equations. So you can use Matlab, you can use Excel VBA, you can use both of them. So before this class ends, we are going to look at how to use either Matlab or Excel VBA to do that. The next method is the Gauss-Seidel method. And for the Gauss-Seidel method is an iterative approach, and giving ax is equal to b, where you want to solve for x. So actually breaking this equation from the matrix form into equation form is given by this. So the step involved in solving using the Gauss-Seidel method is that you have, for instance, if you have three sets of equations given by this, this, and this, where you want to solve for x1, x2, and x3, and you have b1, b2, and b3. So the first step is that you're going to make, for the first equation, you make x1 the subject of formula in order to get this. So we simply made x1 the subject of formula A to get this. So for the second equation, you make x2 the subject of formula. So making x2 the subject of formula, we arrive at this equation A. Then for the third equation, you make x3 the subject of formula. Then you arrive at the last equation. So given your sets of equations, you make x1 the subject of formula using equation 1. You make x2 the subject of formula using equation 2. Then you make x3 the subject of formula using equation 3. Then after that, you are going to assume values for x2 and x3. First of all, you start with 0. So you want to get x1. Then we are going to guess. It's just like the finding the roots of equations, the topic we did last before coming to this topic, is that you're going to guess the values of x2 and x3. So normally we start with 0 for x2 and x3. You're going to start with 0. So you make x2 to be 0. Then you make x3 to be 0. Then you solve for x1. Then to get x2, we already know x1 here. So we put in the value for x1 we solved here. Then our x3 is still 0 because we don't know it. We just guess it at 0. So now we have x1 and x2. So to solve for x3, you're going to put in x1 here, which you solved here. Then you put in x2 here, which you solved here to find x3. So it's an iterative approach. So this is, after doing this is going to be your first iteration. Then you calculate the error like we did previously. You calculate the error, then you'd have a second iteration. You have a second iteration, then third iteration, fourth iteration. Then you keep on going until you reach your last iteration, or until when you are already tired and you are ready to stop. So we are going to use an example to illustrate it. So this is the question we've been considering since, and we know the true values. So for this method, for the Gauss-Seidel method, we need to track the error. So that means that you are going to be giving the true values. So if you are not giving the true values, you're going to calculate the approximate error. So the first step, like we did, is you're going to make x1 the subject of formula using equation 1. So we arrived at this. Then you make x2 the subject of formula using equation 2. We arrived at this. Then we make x3 the subject of formula using equation 3. You arrive at this. Then after that, we are going to solve for x1, x2, and x3. So for x1, you are using this equation, but we don't know x2 and x3 yet. So you make it 0. You put in 0 here, you put in 0. Then you solve for our x1, which we got as 2.616. Then after that, you solve for x2 using this equation. So we know x1 as 2.616, which we are going to put here. But we don't know x3 yet, so we just put 0. Then we'll solve for x2. Then finally, for the third equation, we're going to use this equation. So we know x1, which we got here, and we know x2, which we got here. Then we solve for x3. So that is the first iteration. Then for the second iteration, so we're at the first iteration. Now we are at the second iteration. So it's an iterative method. So the second iteration, you are going to use the same equation, but x1 is the value of the x. So in order to solve for x1, you need x2 and you need x3. So this is our x2 we got previously, and this is our x3 we got previously. So we just put it inside this equation to solve for x1. Then to solve for x2, you need x1 and x3. So we got x1. So you need x1 and x3. So this is our x3 here, and this is our x1. So your new x1 is what you're going to put here. Then you solve for your x2. Then to get your x3, you need x1 and x2. So this is your x1 and this is your x2. We use it to solve for x3. So since it's an iterative approach, we need to calculate the error. And we're given the true values in the question. X1 is equal to 3, x2 is equal to minus 2.5, and x3 is equal to 7. So we can track the error as we go. So for the second iteration, I will track the true error. So this is the true value for x1. So this is the true error for x1, the true error for x2, and this is the true error for x. This is the true error for x3. So we track the error. So we got 0.31 for x1. We got 0.015 as the error for x2. And we got 0.042 as the error for x3. So that should tell you that, remember, the true value for x1 is 3. The true value for x2 is minus 2.5. And the true value for x3 is 7. So that means that the Gauss-Seidel method is a very fast method, because as just the second iteration, our error was really small. So we started, so this is what you're going to do. You're going to start with 0 at the first iteration. You start with 0 as x2 and x3 for the first iteration. But now, at the first time you did it, at the first iteration, you have your new value of x1, so which you're going to put in here, but you don't have x3 yet, so it's still 0. So at the first iteration, but at the third, for x3, you have a new value of, you have x1 and you have x2, which you're going to put in here. So that's the Gauss-Seidel method. So the Gauss-Seidel method is extremely fast and is less computation intensive compared to the other methods we'll be discussing. So if the true value is not given to you, the best approach is to use the estimated error. So remember that our estimated error is the uh, current approximation minus the previous approximation divided by the current approximation. So if the true value is not given, you're going to use the estimated error to track for the error. Then when your error is below a certain uh, percentage, then you can stop. You can stop the iteration. So this is the Gauss-Seidel method. So the last method we are going to be discussing today is the Jacobi's iteration method. So the Jacobi's iteration method is, I think there's no example here, but I'm just going to explain it. It's almost the same thing with the Gauss-Seidel method. The only difference is that for the you're going to maintain the value of the x you have for each iteration. So for the Gauss-Seidel method, for the first iteration, you calculate for x1, x2, and x3. So, but for the Jacobi's iteration method, you maintain the values of the x's you have. So we put 0 here for x2 and we put 0 here for x3. So to get x2, you're going to put in 0 here and you're going to put in 0 here. I'm talking about the Jacobi's iteration now. So to get x3, you're going to put in 0 here and going to put in 0 here. So you will not keep updating the values with the new values you are getting. You're just going to put in a single value throughout. So you're going to get your x1, x2, and x3. So for the second iteration, the values you got in the first iteration, that's what you're going to put in here. They are the same values you got for your x1, x2, and x3. But for the Gauss-Seidel method, which I just described, you're going to keep updating. Like now, when we calculated our x1, we got this. Then to calculate your x2, you need x1. This is the x1, and this is the x3. But using Jacobi's method, is the x1 you calculated in the first iteration you're going to use. You're not going to use the current value at the current iteration. Is the values at the previous iteration you're going to use. So for the Jacobi's method, you're going to use this x1 at the first iteration, not at this particular iteration. Then x2, x3 at the first iteration. Then to calculate x3, you're going to use x1 at the first iteration, not this particular x1. You're going to use x2 at the first iteration, not this particular x2. So that's just the difference. But the 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 Jacobi's iteration method is really slow. It converges very, very slowly. So that's why I did not even bother to actually solve it. The Gauss-Seidel method is actually much more superior than the Jacobi's iteration method because it converges very, very quickly and it's very faster than the Jacobi's iteration method. So those are the methods we are going to be we have considered so far for solving linear algebraic equations. So remember when I was discussing about the LU decomposition, and I was saying that the LU decomposition method is actually much more computational intensive because you have to do three things. You first of all have to decompose the A matrix, then you do forward substitution to get D, then you do backward substitution to get X. And the first reason I explained is that you can actually use it to get the inverse of the matrix. And another reason is that, another very interesting reason while the LU decomposition method is much more superior than the Gaussian elimination method, which we discussed last week, is because if you have a question whereby your A matrix is constant, it doesn't change, but it's only your B matrix that is changing. So your A matrix is the same thing. It's only your B matrix that changes. So the A matrix is constant, it doesn't change, but the B matrix changes. So if you use the LU decomposition, since the A is constant, so you know that you already have your L and your U. All you just need is to get your to do this forward substitution and backward substitution. You don't need to decompose it again, because for another value of B, which is changing, all you just need, since you've already decomposed A into L and U, all you need to do now is to just solve for D here, because your B is changing, and after that you solve for your X. So that's uh, the second advantage of the LU decomposition. So I'll just go over it again. The second advantage of the LU decomposition is that if you have a question in which the A matrix is the same, it doesn't change, but is your B matrix that is changing. So you've already decomposed your matrix into L and U. You've decomposed the matrix into L and U. So all you need to do now is just these two steps. So in essence, you've just skipped this first step. There's no need for decomposing another A matrix. For instance, given this question we started with, so this is our A matrix and this is our B matrix. So if there was another question that made use of this same A matrix, but this B matrix was different, so since you already have L and U, you've decomposed this A matrix into L and U, you don't need that decomposition step anymore. All you just need is the forward substitution step and backward substitution step, and you are done. I think there's a question. Okay. All right. So that's okay, Jamil, I saw your message. It's noted. Okay. So that's the advantage of the LU decomposition method. So let me refer you to an example in the textbook. Let me share my screen. Okay. So this example 9.11 in the textbook is in this question is saying that an electrical engineer is supervising the production of electrical components. Then in the production of those electrical components, you have these components in that manufacturing plant. They are manufacturing three different components. But in order to manufacture it, they need, for the first component, they need 15 grams of metal, 0.3 grams of plastic, and 1 gram of rubber to manufacture the first component. To manufacture the second component, you need 15 grams of metal, 0.4 grams of plastic, then 1.2 grams of rubber. Then to manufacture the third component, you need 19 grams of metal, 0.55 grams of plastic, and 1.5 grams of rubber. And for the total quantity of items of the metal, plastic, and rubber are this. So this question is actually solving, you can convert this question into solving algebraic equations. Well, these values are highlighted, apart from these ones, are your A matrix. Then these values here that is highlighted are your B matrix. So you need to just solve for x1, x2, and x3. So those values you solve for are the components that can be produced per day. So this question is actually an application question. So I would encourage you to it's not an assignment, it's just like a classwork or lesson. I would encourage you to solve it. So it's question 9.11. So this question is actually solving for the linear algebraic equation. So this is your A matrix. The one I highlighted is your A matrix, and these values are your B matrix. So I'm telling you that the LU decomposition method is good when you just have, when your A matrix is constant. Like in this particular question now, as an electrical engineer, you want to manufacture these components. And to manufacture these components, these are the quantities you need, like it's fixed. For these components, you just need to manufacture the first component. These are the parameters you need. But these are the quantities that are available. So in this particular question, the A matrix doesn't change because like it's a standard. To manufacture component one, you need this, which doesn't change. To manufacture component two, you need this combination of engineering materials. To manufacture component three, you need this composition on the last row of engineering materials. So this is our A matrix. It doesn't change. Like that is the production step. But the quantities that are available in that particular company is changing. Like for instance, in a particular day, they may have these quantities available. For the next day, it might increase or it might decrease. So this is an application where the LU decomposition method is best for solving for this particular question, because you know that your A matrix doesn't change. So you already have your L and your U. You've already decomposed this A matrix here into L and U. You don't need that step anymore because it's constant. Like to manufacture it, this is the particular combination you need. So it doesn't change. But it's this combination, the B matrix, that is changing. So these are the quantities that are available in that particular factory. So these quantities are changing. They may increase or decrease depending on the particular day. So you just need to solve for how many components that can be produced. So if, for instance, if you are working in this factory and you've already decomposed this A matrix into your L and U, so in order to know how many components that can be produced, given these quantities that are available, you don't need to go back and solve and decompose your A matrix because it's already constant. It doesn't change, so you already know it. All you just need is the forward substitution and backward substitution step in order to get the number of quantities that are available. So I hope you understand that. So that is one of the advantage of the LU decomposition. It has more computation steps compared with the Gaussian elimination method. But once you've decomposed your A matrix into L and U, then if these big quantities are changing, then it's just going to be very, very easy to do that. So I'm encouraging you to solve this question. You can use Gauss elimination method, Gauss method. You can use the LU decomposition method. You can use the Gauss-Seidel method. You can use the Jacobi's method. So I'm actually helping you by showing you this example. So try to solve it. It's just an advice I'm giving you. So just try to solve this question on your own. So let me move back to the notes. Okay, so we've done that. So the last part of this class is to use software packages to solving algebraic equations. So we already know that it's actually very tedious to solve these equations by when you're using manual calculation or by hand. So obviously there should be a software approach to solving it. So we are going to make use of Excel and we'll make use of Matlab. We already use Matlab when we're doing modern control, so you might be able to do that. But I'm going to talk about Excel and Matlab just for the purpose of completeness. So if you have an equation, AX is equal to B. So if you have AX is equal to B, if you have AX is equal to B, you can just solve for X by doing the inverse of A multiplied by B. So this is the strategy we are going to be employing in solving for X using software approaches. So I'm going to go to Excel. So how do you use Excel to solve linear algebraic equations? So I'm in Excel now. So this is the A matrix in the question, and this is our B matrix in the question. So in Excel, there's a function called the M inverse. So the M inverse is used to calculate the inverse of the matrix. Then after getting the inverse of the matrix, then if you multiply it by B, you can solve for X. So you are going to be using, you first of all calculate the inverse of the matrix. So this is the matrix. You want to calculate the inverse. So to do that, we just use this function, M inverse. M inverse. Then you select the array. So the array is from B1 to D3. D3. So you're telling Excel that you should find the inverse of this matrix that is from B1 to D3, which is already selected. Then you're going to use Control Enter, Control Shift Enter. So you press your Control Shift Enter, then it's going to give you the inverse. So this is the inverse of the matrix. Then to get the X, which we're actually solving for, we'll multiply the inverse of A times B to get the X1, X2, and X3. So when you're going to select all the cells where you want your X1, X2, and X3 to be, then you say equal to, there is a function in Matlab called mmult, which is just to multiply. So we are multiplying the inverse of A. Then the inverse of A is from B5 to D7. You are multiplying it with this B matrix, and your B matrix is from F1 to F3. So this is your A inverse, and this is your B matrix. So we want to solve for X now. And to solve, you just press Control Shift and Enter. So this is your X1, X2, X3. So this is another example. This is the one we've been considering in this class. So this is the A matrix. This is the example we've been using, and this is our B matrix. So similar to what we did previously, you're going to find the inverse of A first of all. So you select all the cells where you want the inverse to be. Then you say is equal to M inverse. Then, so the A is from B11 to D13. So D13. Then you press Control Shift and Enter. So this is the inverse of the A matrix. Now to get your B matrix, you would highlight all the columns where you want your solution to be. Then you multiply your inverse and the B matrix. So is equal to, so we use the mmult function, mmult. So you are multiplying the A inverse, which is from B15 to, which is from B15 to D17. Then you're multiplying it with your B, which is from F11 to F13. So then you press your Control Shift and Enter. So this is your x1, x2, and x3. If you can remember, this is the x1 we got in the question. This is our x2 we got in the question. And this is our x3 we got in the question. So now we know how to calculate it using okay, you said I should select A6. So this is A6. This is A6. I just simply typed it. So this is just typing. So I just typed A here, then inverse. So yeah, I just formatted it to subscript, to superscript. You inputted the inverse of A. Okay. Please now select A6. Okay, all right. So this A6 is what I typed. Then I formatted it to superscript so that it's going to be raised to power minus 1. That's what I did. So this is using Excel to solve algebraic equations. Now we're going to go to Matlab now to solve for algebraic equations. So in order to do that, would specify our A and our B matrix. So you already know how to do that. So this is, for the question, this is the A matrix. So this is the first row, second row, third row, and this is the B matrix. So this is our A and our B matrix. Then to get the X, there are two methods. You can use the left division method. So A, then this is the left division operation. It's not of, this is the left backward slash, it's not the forward slash. So it's called the left division operation. So once you do this, you will get your A. Now, another method is that you can just say the inverse of A multiplied by B, which was kind of the method we were using in Excel. So if you do that, you would arrive at the same answer. Then for the second question, the one we've been considering in this class, so this was our A matrix. This is the first row. This is the second row. Then this is the third row. Then this is our B matrix here. So this is our A matrix and this is our B matrix. So remember that for your A matrix, this is the first row. In Matlab, to go to the next row is a semicolon. Then this is the second row. To go to the next row is a semicolon. Then for your B matrix is a column vector. It's just a single column. So this is the first element. Then you go to the next row. The second element, go to the next row, the third element. Another way you can write your B matrix is that you just write it as a single row vector. So this is a single row vector, but you put a transpose so that it's going to become a column vector. If you just use it like this without the transpose, is a row vector, but the one we're using is a column vector, so it has to be a transpose. Then to get X, you can just use the left division operation, which is this. So this is our x1, x2, and x3. Or you can just use the inverse of A, then multiplied by B. So we arrived at the same answer for x1, x2, and x3. So these are the, this marks the end of the class on. Okay, there's a question. The first Matlab question refers, I don't understand where adding values. Okay, thank you for that question. It's because that matrix in the question is an Ebates matrix. So let me just write it again. It's an Ebates matrix and is a kind of matrix. So this is the B, this is the A. So A is given by this coefficient. So if you look at it, you will know that there's some structure there. So there's 1 divided by 2, then 1 divided by 3, then there's 1, 2 divided by 3, then 1 divided by 2, then 1, 3 divided by 4, and 3 divided by 5. It's a special kind of matrix called the Ebates matrix. Then the B matrix is just you add all the elements in the first row. Then here we are adding all the elements in the first row to get your B1. Then your B2, we are adding all the elements in the first row, in the second row, sorry, to get this. Then for this, we are adding all the elements in the third row to get this. So it's called the Ebates matrix. It's a special kind of matrix. And one property of this matrix is that when you solve for x, the result is going to be 1. If you see when we solved for x, we got 1, 1, 1 as x1, x2, and x3. So it's a special kind of matrix. So thank you for that observation. So it's just it's a special kind of matrix that is of this form, such that when you solve for it, so an Ebates matrix is a kind of matrix that such that the solution for the x1, x2, x3 is 1. So that's how we formulated the problem. So that's why we had this the B in this form. So it's just for illustration purpose. Okay. So that this class marks the end of solving algebraic equations. We've completed the class. So in the next class, we are going to move into another topic. Yeah. Okay. What's the name of the matrix? Okay. The name of the matrix is, let me just type it here. It's an Hilbert matrix. That's the name. Hilbert. Is an Hilbert. That's the name. Sorry if I'm not pronouncing it very well. So that's the spelling. So it's a kind of matrix that is actually of this form. Then the solution to the matrix is 1, 1, 1. Okay. All right. So as I was saying, that this class marks the end of solving algebraic equation. As a way to help you, please just try to solve this question, right? Using all the methods we've talked about in this class. The question is very important. Just try to solve it. It's not an assignment. Then in the next class, we are going to move on to another topic entirely, which is curve fitting. So we are gradually coming to an end of this course. So in a few weeks time, we'll just end the course. So thank you all for joining me. We're going to see next week.